right now, tucked into the pocket of your winter coat, or maybe, I don't know, shoved into the bottom of a hiking backpack, you might actually be carrying around a miniature, highly engineered chemical reactor.
Yeah, and the crazy part is that it runs on the exact same destructive science
Mm.
that, eats away the undercarriage of old cars or degrades abandoned bridges.
It's wild to think about. Welcome to the deep dive. Our mission today is to take something entirely mundane, a disposable heat pack. You know, the kind you buy at a convenience store to survive a freezing commute or maybe to soothe a sore muscle. And we're going to unpack the surprising, elegant science hidden right inside of it.
Right, because we look at a small, slightly crinkly paper pouch, and we just see a simple winter staple. But it generates reliable, intense warmth for hours on end. And it does this without a single battery, no wires, no moving parts.
Nothing.
Right, nothing. It relies on a very precise application of physical chemistry and thermodynamics,
Yeah.
all disguised as this cheap disposable product.
And that contrast between the unassuming packaging and the complex engineering is really what we are digging into today. We are essentially just casually carrying around these miniature chemical engines in our pockets.
Exactly.
But before we crack open the pouch to look at the chemistry of what is actually happening at a molecular level, we need to understand how these packs are designed to operate in the real world. So, our source material points us to Japan to understand the operating parameters, because that's really where this specific iteration of the technology was perfected.
Yeah, they are completely ubiquitous there. In Japan, these disposable heat packs are generally known as Kairo, and the documentation highlights two distinct variations that really dominate the market.
Right.
The first is the Haranai Kairo, and this is your standard non-adhesive hand warmer. It's the type of pouch you just loosely toss into your gloves or keep moving around in your pockets to keep your fingers warm.
But the more interesting engineering challenge comes with the second type, right?
Yeah.
The Haru Kairo.
Yeah, exactly.
Haru translates roughly to stick on or adhesive, and these are designed with a peel-off backing so you can attach them directly to an inner layer of your clothing. But the documentation for the Haru Kairo comes with this massive bold print safety protocol.
Oh, yeah. It's very serious about this.
Right. It says you must never, under any circumstances, apply the adhesive side directly to your bare skin.
And the thermal output totally dictates that warning. A Haru Kairo is engineered to sustain an average temperature of 52 degrees Celsius.
Which is, wait, let me be the math. That's roughly 125 degrees Fahrenheit.
Exactly, 125 degrees. And it doesn't just, spike to that temperature and slowly cool off. It is engineered to sustain that intense 52 degrees for up to 8 continuous hours.
Wait, I need to pause on that spec, because 8 continuous hours at 52 degrees Celsius is no joke. That is a massive amount of sustained energy. I mean, when you put on a down jacket or a thick pair of wool socks, you are just trapping your body's own natural metabolic heat.
Right, the jacket isn't doing any actual work.
Yeah, exactly. The jacket itself isn't doing work, but this little paper packet isn't trapping anything. It is actively generating a continuous flow of new thermal energy. How on earth is a handful of dry powder in a paper sleeve doing that without a power source?
Well, the energy generation comes from a chemical reaction we normally associate with decay and neglect rather than comfort.
Okay.
The fundamental science driving the heat pack is oxidation, specifically the oxidation of iron powder.
Which means we are talking about rust.
We are talking about rust. The comforting warmth radiating into your hands on a freezing day is literally just rusting metal.
That's mind-blowing.
On a chemical level, when oxygen interacts with iron, the atoms bond to form iron oxide. And that specific chemical bonding process is exothermic.
Exothermic meaning the reaction releases excess energy into the surrounding environment in the form of heat. But, okay, I have to push back on the physics here. Because if oxidation releases heat, why doesn't my heavy cast iron skillet get blazing hot when I accidentally leave it wet in the sink and it rusts overnight? I mean, I have never touched a rusty piece of metal and burned my hand. Why is the heat only palpable in this little paper pouch?
That's a great question. So think about your cast iron skillet. It is a massive, solid block of metal. The surface area to volume ratio is incredibly low.
Oh, okay.
Only the iron atoms on the very, very outer skin of the pan are exposed to the oxygen in the air. So the chemical reaction is happening, and it is technically releasing heat.
Yeah.
But it occurs so slowly and over such a small relative surface area that the thermal energy just dissipates into the room air instantly.
You just can't feel it.
Right. You can't feel it because the rate of energy release is microscopic compared to the sheer size of the object.
So if I am walking down the street and I see like an old rusty bicycle chained up to a fence in the rain,
Yeah.
you're telling me that rusting metal frame is technically releasing heat into the air?
It is absolutely radiating heat. I mean, the total amount of energy released over the years it takes for that bicycle frame to rust completely away is actually substantial.
Wow.
The heat pack simply takes that exact same decay process and manipulates the physical properties of the iron to force it to happen at an incredibly accelerated rate.
And that manipulation is why the pouch contains iron powder, not just a solid chunk of iron. By grinding the iron down into microscopic dust, the manufacturer is dramatically changing that surface area to volume ratio.
You increase the exposed surface area by factors of thousands. Instead of a slow trickle of oxidation happening on the surface of a solid block, you have billions of individual iron atoms reacting with oxygen simultaneously.
It's like putting the rust on fast forward.
Exactly. The massive increase in surface area concentrates all of that potential energy release into a very short, intense burst of heat.
So we are just walking around holding a pouch of hyperspeed rust.
Pretty much.
But even with the powdered iron, if I just take a handful of iron shavings and leave them in a pile on my kitchen counter, they aren't going to suddenly jump to 52 degrees Celsius and stay there for my whole workday.
Yeah.
Simply mixing iron powder and air still won't give you that reliable 8-hour burn.
No,
Warm.
the iron powder needs a facilitator to initiate the oxidation. If you look at the internal recipe of the pouch, the next necessary ingredient added to the dry mixture is water.
Okay, moisture.
Yeah, moisture is a strict requirement for the oxygen and iron atoms to actually begin sharing electrons effectively and forming those iron oxide bonds.
But water alone still isn't fast enough. Like a wet shovel left in the yard still takes weeks to rust, not seconds. If we need this packet to reach 125 degrees Fahrenheit the moment we step out into the snow, there has to be something hitting the gas pedal on that electron transfer.
And there is. The reaction requires an electrolyte solution to lower the electrical resistance. See, the oxidation process involves the movement of electrons from the iron to the oxygen. Pure water is actually a relatively poor conductor.
Right.
But by introducing salt into the mixture,
Salt?
the sodium and chloride ions dissolve into the moisture, and that creates a highly conductive pathway for the electrons to travel.
Oh, wow. This perfectly explains why the undercarriages of cars rust out exponentially faster in regions where the roads are heavily salted during the winter. The salt water is acting as a chemical accelerator pedal.
Exactly. The salt pushes the oxidation process into absolute overdrive. It facilitates the electron transfer so efficiently that the exothermic reaction happens rapidly and the heat generation becomes immediate and palpable.
Okay, so we have a reactive fuel, we have powdered iron, and we have deliberately saturated it with water and salt to hyperaccelerate the electron transfer. But this creates a huge engineering problem, doesn't it?
It creates a massive one.
Right, because if we just mix those three things together, why doesn't the pouch instantly flash rust? I mean, it seems like it should get dangerously hot for about 5 minutes, completely melt the nylon lining of my pocket, and then just burn out.
You're totally right. A mixture of only iron, water, and salt would result in a flash fire of oxidation. You would get unmanageable localized heat that drops off almost immediately as the accessible iron is consumed.
So how do they stop that?
Taming that chaotic energy to stretch it over an 8-hour period requires very specific thermal regulators inside the pouch.
And the first of those unsung heroes inside the recipe is activated carbon, right?
Yes, activated carbon. And what's interesting is it plays no part in generating the heat itself. Its role is entirely about management.
Okay.
The material is engineered to be incredibly porous. Under a microscopic lens, it resembles a dense network of caves and tunnels, which gives it a massive internal surface area. But crucially, activated carbon is also highly thermally conductive.
So it functions as a thermal distribution network.
Exactly.
Because without it, the moisture and salt might pool in one corner of the pouch, causing the iron there to react violently while the rest stays cold. You would just have a scorching hot lump burning your leg.
Right. The activated carbon conducts the thermal energy away from the fastest reacting iron particles and spreads it evenly throughout the entire dry mixture.
So the carbon ensures the entire physical surface of the packet radiates warmth uniformly?
Yep. But even with perfect distribution, the heat would still radiate away into the freezing winter air way too quickly. The system requires an internal insulator to capture the thermal energy and throttle its release into your pocket.
And this brings us to the most surprising ingredient in the entire source stack. When I read this, I had to double check it.
It's so weird, right?
It is vermiculite. For anyone who spends time at a garden center, vermiculite is that very lightweight, flaky, slightly shiny mineral you buy in massive bags to mix into potting soil.
Yeah, the exact same stuff.
It helps aerate the dirt and retain moisture for seeds. It is bizarre to find a gardening supply sitting inside a chemical reactor.
It seems out of place, but vermiculite is actually a hydrated magnesium aluminum silicate. And the reason it is so useful here stems from how it's processed in the factory.
Okay, how do they process it?
Well, raw vermiculite is subjected to extreme, rapid heat, which causes the trapped moisture inside the mineral to basically turn to steam.
Oh, so it pops.
Yes, the mineral expands violently, almost exactly like popcorn, separating into numerous, incredibly thin layers.
And that expansion process creates thousands of microscopic pockets of trapped air between the layers of the flaky mineral.
Exactly, and those trapped air pockets turn the vermiculite into an exceptional thermal insulator.
That makes so much sense.
Inside the heat pack, the vermiculite essentially wraps the aggressively oxidizing iron in a thermal blanket. So while the salt accelerates the heat generation and the carbon distributes it evenly, the vermiculite traps it, restricting the flow of the thermal energy outward.
It transforms a rapid chemical spike into a steady, comforting, long-lasting burn.
Yes, it's a brilliant synergy of materials. You take the chaotic, accelerated rust caused by the salt, and you tame it with gardening soil and charcoal.
That is just so elegant. But wait, even with this perfectly balanced internal recipe, even with the water, salt, carbon, and vermiculite perfectly proportioned, if we took that mixture and dumped it into a bowl on the table, it would still react entirely too fast, wouldn't it?
Oh, absolutely.
Yeah.
Because the open atmosphere provides an unlimited, uncontrolled supply of oxygen.
Right.
So the final control mechanism preventing a flash reaction isn't chemical at all. It is physical. The container holding the powder is doing just as much engineering work as the powder itself.
Okay, so let's talk about the pouch, because it is not just cheap, fuzzy paper like it feels. It is a highly specialized membrane. And the defining feature of this membrane is that it is riddled with microscopic pores.
Right, and the diameter and density of those microscopic pores dictate the exact diffusion rate of oxygen gas into the pouch.
Because oxidation requires a continuous supply of oxygen molecules to proceed.
Exactly. The membrane acts as a deliberate physical bottleneck.
It is exactly like the throttle on a car engine, or like a dimmer switch on a light. The chemical engineers have calculated precisely how much oxygen is required to maintain a steady 52 degrees Celsius reaction. By designing the pores to a specific microscopic size, they physically restrict the volume of oxygen molecules that can pass through the membrane at any given second.
The chemistry inside is primed and ready. The electrolyte solution is facilitating the potential electron transfer, but the reaction can only proceed as fast as the membrane allows new oxygen molecules to enter.
That is brilliant.
It really is. The physical packaging literally forces a reaction that wants to sprint into an 8-hour marathon.
And you know, this physical mechanism finally solves the most obvious mystery about these heat packs for me.
Which is?
Well, it explains why they remain completely dormant while they're sitting on the shelf at the convenience store or just rolling around in the bottom of your glove box for 6 months.
Oh, right. Because they are sealed inside a completely airtight outer plastic wrapper.
Exactly. That outer wrapper creates a localized vacuum environment. As long as the pack is inside that plastic, zero atmospheric oxygen can reach those microscopic pores on the inner membrane.
The chemical engine is completely starved of the one gas it needs to run, so
Yeah.
the electron transfer is just totally suspended in animation.
But the second you tear open the plastic wrapper and pull the paper pouch out,
Atmospheric oxygen rushes against the membrane.
yep, it squeezes through those microscopic pores, makes contact with the damp, salty iron powder, and the reaction fires up. The user breaking that vacuum seal is literally the activation switch. Gas diffusion begins, and the physics of the exothermic reaction take over automatically.
It's so cool. Putting all these individual pieces together completely changes the way you look at this everyday item.
It really does. I mean, the next time you pull out a disposable heat pack for a winter walk, or maybe you grab one to soothe an achy joint, you're no longer just looking at a simple warm pouch.
No, you are holding a carefully calibrated system of accelerated decay. One that utilizes surface area manipulation, electrolyte-driven electron transfer, and precise gas diffusion throttling.
You are initiating a perfectly insulated, microscopically throttled, high-speed rusting event right in the palm of your hand.
It is a stunning example of human ingenuity. We've taken a completely natural process, one that is slow, destructive, and usually degrades our infrastructure, and we've figured out how to harness its energy release for our own therapeutic comfort.
It's incredible. And, that ability to isolate a natural reaction, break down its components, and rebuild it to serve a specific purpose, it's the hallmark of modern materials science.
Absolutely.
It leaves you looking at the world a little differently, doesn't it? I mean, think about it. If we can so elegantly harness something as mundane, as slow, and as completely invisible as the rusting of iron, and if we can manipulate that decay to generate reliable, portable, battery-free heat for hours on end, what else is out there? What other slow, invisible chemical reactions are happening all around us right now? In the soil, in the air, in the decay of natural materials? And what might we eventually figure out how to capture, throttle, and use for personal energy in the future?
That's a great question.
Just something for you to ponder the next time you're standing in the freezing cold waiting for that little paper pouch to warm up. Thanks for joining us on this deep dive.